The Wehrmacht testing officer at Hillesleben Proving Grounds checked his stopwatch again, certain he'd made an error. It was early 1943, and the olive-drab Howitzer sitting on the firing range had just completed another cycle. 8 rounds, 60 seconds. He looked at his colleagues, experienced artillerymen who'd served from the Polish campaign through 2 winters in Russia. No one spoke immediately. They'd all seen the same thing, counted the same shells, timed the same interval. Finally, someone said what they were all thinking. This shouldn't be possible. Not with a 105mm howitzer. Not with any field gun they'd ever encountered. The weapon in question was an American M2A1 105mm howitzer, captured somewhere in North Africa and shipped back to Germany for evaluation. Standard procedure for any significant enemy equipment: test it, measure it, document everything, distribute reports to ordnance bureaus and field commands. But this test was producing results that didn't fit any existing framework for understanding field artillery. 8 rounds per minute wasn't a burst rate, some desperate crew pushing equipment past safe limits for a few frantic seconds. This was sustained fire, the rhythm a properly trained crew could maintain for extended periods. The German test team had assembled their own veteran gunners, men who knew artillery inside and out, and walked them through the American drill procedures using captured training manuals. The numbers held up. 4 to 6 rounds per minute was easily achievable. 8 rounds per minute was possible with a skilled crew. The M2A1 didn't just match German field artillery performance, it doubled it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. You might assume this is simply another tale of American industrial superiority. More equipment, more resources, more of everything flooding the battlefield. But what unsettled these German officers went deeper than logistics. Rate of fire in field artillery isn't a luxury specification. It's the difference between suppressing an enemy position before they can respond and arriving 30 seconds too late when your own infantry is already pinned down. It's the gap between breaking up an enemy attack before it reaches your lines and watching that attack roll through because you couldn't deliver enough steel fast enough. German artillery doctrine in 1943 remained rooted in traditions, extending back to the Great War, refined through interwar study and early World War II campaigns. The emphasis was methodical accuracy, careful observation, precision fire control. Their standard light field howitzer, the 10.5 cm leichte Feldhaubitze 18, leFH 18, was a proven, reliable weapon, Krupp engineered, respected across every front where German forces fought. It could fire 4 to 5 rounds per minute under optimal conditions with an experienced crew working in perfect coordination. But optimal conditions were increasingly rare by 1943. The M2A1 sitting in front of these officers was clocking 8 rounds per minute with consistency that didn't seem to care whether the crew was composed of veterans or men fresh from training. The weapon itself enabled the performance. That's what made the German test team fall silent. This wasn't about individual gunner skill or superior training. The capability was engineered into the weapon from the ground up, designed into every mechanical system and crew drill sequence. The Americans had built a field howitzer that operated on a fundamentally different clock than anything Germany fielded. The context surrounding this discovery matters enormously. By early 1943, the Wehrmacht was fighting a multi-front war of attrition it couldn't win through tactical skill alone. Every shell counted, every minute of fire superiority counted. And across North African battlefields, American and British gunners were systematically drowning German positions in artillery fire faster than German guns could respond. Forward observers from Afrika Korps units had been filing reports for months about the sheer volume of Allied artillery fire. Not just more guns, though the Allies certainly had numerical superiority, but individual Allied batteries that seemed to fire continuously while German batteries worked through their methodical fire sequences. This test, conducted in the controlled environment of a proving ground far from any front line, confirmed what German observers had been reporting. The Allies weren't just bringing more artillery, They were bringing artillery that fundamentally operated faster, enabling tactical and operational advantages that German doctrine couldn't easily counter. The psychological impact on the testing officers would have been immediate and profound. They'd spent careers perfecting a system, a doctrine, a comprehensive approach to indirect fire. And here was a mass-produced American weapon, built by a nation that barely maintained a standing army in 1939, outpacing the pride of Krupp engineering on the single metric that mattered most in modern mobile warfare. The rate of fire gap wasn't immediately obvious when you compared specification sheets. On paper, German and American light field howitzers looked roughly comparable. The leFH 18 fired a 14.8 kilogram high-explosive shell out to 10,600 meters maximum range. The American M2A1 lobbed a 14.97 kilogram projectile to 11,270 meters. Range advantage existed but wasn't catastrophic. Shell weights were nearly identical. Both were towed weapons requiring a prime mover, typically a truck or half-track. Both used similar propellant charge systems. Both operated with 6 to 8-man crews. On static comparison charts filed away in ordnance bureaus, these appeared to be peer weapons serving similar roles. But wars aren't fought on specification sheets filed in Berlin offices. They're fought in 6-minute fire missions, where the side that puts more steel downrange in less time controls the tactical outcome. Wehrmacht artillery crews in 1943 were still trained under standards developed in the 1930s, refined through campaigns in Poland, France, and the early years on the Eastern Front. The doctrine emphasized precision and fire discipline. Every shot was planned and purposeful. Fire missions followed rigid sequences that had been proven effective in earlier campaigns. The process began with observation. Forward observers identified targets, calculated coordinates, and transmitted data to fire direction centers. Next came registration, deliberate ranging shots adjusted until they bracketed the target. Only after successful registration did the fire for effect phase begin, and even then, German batteries fired in careful, deliberate patterns designed to maximize accuracy and conserve ammunition. The leFH 18's crew drill reflected this methodical philosophy. The breech operator opened the breech block manually after each shot, a horizontal sliding wedge mechanism that required deliberate physical operation. The loader and assistant loader man handled the shell into the chamber, a 14.8 kilogram projectile that required careful handling. The fuse setter adjusted each round individually based on the target's range and the desired burst pattern. The gun commander verified everything before calling for fire, checking elevation, traverse, and ensuring the crew was clear of the recoil path. Under ideal conditions, with a rested crew facing no incoming fire and possessing proper ammunition supply, a good German battery could manage 4 to 5 rounds per minute per gun. Exceptional crews with perfect coordination occasionally reached 6 rounds per minute for brief periods. But ideal conditions were increasingly rare by 1943. Crew fatigue from continuous operations, inexperienced replacements filling casualties, ammunition shortages, limiting training opportunities, and constant Allied air harassment meant real-world rates often dropped below 4 rounds per minute. American artillery training had evolved along a completely different path. The United States Army Field Artillery School at Fort Sill, Oklahoma, had been refining its methods since the 1920s, studying Great War lessons and developing doctrine for future conflicts. But the massive expansion after 1941 forced rapid standardization around principles of speed and volume. Fort Sill instructors were teaching tens of thousands of new artillerymen, most of whom had never seen a howitzer before Pearl Harbor. The doctrine had to be simple enough for rapid training, yet effective, and enough for modern warfare. The solution was mass fires, multiple batteries hitting the same target simultaneously with overwhelming volume. Officers learned that properly coordinated mass fires could shatter enemy formations before they had time to maneuver or take effective cover. But that doctrine required guns capable of pumping out shells fast enough to maintain continuous suppression. A slow-firing weapon, no matter how accurate, couldn't deliver the shell density that American doctrine demanded. The M2A1 105mm howitzer, which entered production in 1941, was designed around this requirement from its inception. Its breech mechanism used an interrupted screw design with semi-automatic operation. After firing, the breech opened automatically and ejected the spent cartridge case without manual intervention. The loader could immediately insert the next round without waiting for breech operation to complete. This single feature cut several seconds from each reload cycle. The recoil system used hydro-pneumatic buffers, hydraulic fluid to absorb recoil energy, and compressed air to return the barrel to battery. This system was faster and more consistent than the spring and oil mechanisms common in older designs, and it required less maintenance under field conditions. The carriage used a split trail design, two trails that spread apart to provide a wide, stable firing platform and extensive traverse arc. American crews could shift fire between multiple targets without repositioning the entire gun, simply by traversing the barrel within the carriage's broad arc of movement. Every element of the M2A1's design prioritized speed and ease of operation. Crew training at Fort Sill emphasized rhythm and repetition. Instructors drilled students until 6 rounds per minute became muscle memory, not heroic effort. The faster crews, those with natural coordination and intensive practice, could reach 8 rounds per minute sustained. This wasn't considered exceptional performance requiring special commendation. It was simply good crew drill, the standard that American artillery was expected to meet. British gunners operating similar weapons had reached comparable conclusions through their own experience. The North Africa campaign taught Commonwealth forces that German accuracy meant nothing if you could silence their observers with overwhelming volume before they could effectively direct fire. By 1943, British artillery doctrine explicitly prioritized rapid, sustained fire over pinpoint accuracy in most tactical situations. When the German test officers at Hillersleben watched that captured M2A1 run through its paces, they weren't just observing a faster gun. They were seeing the physical manifestation of a completely different philosophy about what field artillery was supposed to accomplish on a modern battlefield. The design differences between German and American howitzers reflected the opposite, lessons two nations had drawn from World War I. Germany emerged from that conflict convinced that artillery had been too crude, too wasteful, too reliant on sheer volume rather than precision. The solution, in the view of German military theorists, was better fire control, superior optics, more rigorous training, and weapons optimized for accuracy. When Krupp engineers began designing what would become the leFH 18 inches the late 1920s, they built a weapon optimized for precision fire under the constraints of Versailles Treaty limitations that had temporarily restricted German armament development. The gun carriage used a box trail design, a single rigid trail that kept the weapon exceptionally stable during firing but limited traverse to just 11 degrees without repositioning the entire gun. You couldn't quickly shift fire to a new target. Every significant adjustment required moving the weapon. The recoil mechanism was reliable but conservative, using a combination of spring buffers and hydraulic dampers that worked dependably, but took time to return the barrel to battery after each shot. The breech was a horizontally sliding wedge block, manually operated by turning a handle. It was robust, it was precise, it sealed reliably, even after thousands of rounds. But it was also slow. Every element of the leFH 18 design assumed that well-trained crews with superior optics and fire control systems would make the decisive difference. The sighting system was excellent. German optics were world-class throughout the war, but adjusting elevation and traverse required careful hand-wheel operation by dedicated crew members. The ammunition was superb, with quality control that ensured consistent shell performance across different production batches. But each shell had to be individually handled, fuses manually set based on range and desired effect. The gun could fire different propellant charge combinations for different ranges, giving it considerable flexibility, but that flexibility came at the cost of complexity. Each charge selection required verification, each fuse setting required calculation and adjustment. Crew training emphasized doing everything correctly rather than doing everything quickly. This approach worked brilliantly during the campaigns of 1939 through 1941, when German artillery supported rapid mechanized advances. Polish, French, and initial Soviet resistance collapsed before German combined arms operations, where artillery played its assigned role effectively. German guns rarely faced sustained counter-battery fire because enemy artillery was either destroyed, captured, or retreating too rapidly to organize effective response. But by 1943, the operational environment had changed completely. Static fronts, attritional warfare, and increasing Allied air superiority meant German guns needed to fire their missions quickly, then displace immediately before enemy counter-battery fire arrived. The leFH 18's methodical design philosophy, born from lessons of precision and economy, had become a tactical liability in a war that increasingly rewarded speed and volume. American engineers had approached the same field howitzer requirement from a completely different philosophical and practical perspective. The M2A1 program began in 1940 when the United States Army recognized that its existing 105mm guns were obsolete. The design team at Rock Island Arsenal studied both French and British designs, incorporating lessons from European warfare while adapting them to American manufacturing capabilities and tactical requirements. The result was a weapon built explicitly for mass production and ease of use. The carriage used a split-trail design that had proven effective on various artillery pieces. Two separate trails spread apart, giving the gun a 46-degree traverse arc without repositioning. This single feature meant American crews could engage multiple targets faster than German crews who had to physically shift their entire gun between targets separated by more than a few degrees. The M2A1's recoil system used hydro-pneumatic buffers with compressed air recuperators. When the gun fired, hydraulic fluid absorbed the recoil energy smoothly, and compressed air automatically pushed the barrel back into battery position. This system was faster than spring mechanisms, more consistent across varying temperatures and conditions, and required less frequent maintenance even under intensive use. The breech mechanism represented the real breakthrough in practical terms. It used an interrupted screw design, similar to systems developed during World War I, but refined to the point of exceptional reliability. The key innovation was semi-automatic operation. After firing, gas pressure automatically opened the breech and ejected the spent cartridge case. The loader could immediately insert the next round without waiting for manual breech operation. The gun commander simply closed the breech and fired. This semi-automatic feature wasn't revolutionary technology in the abstract sense. Various nations had experimented with similar mechanisms for decades, but American engineers refined the system until it worked reliably under field conditions with minimal maintenance, and they integrated it into a weapon designed from the start to exploit the speed advantage it provided. The M2A1 used semi-fixed ammunition, a brass cartridge case containing the propellant charge with the projectile loaded separately. This configuration allowed some flexibility in charge selection while maintaining rapid loading. The cartridge cases were standardized and easy to handle. Crew positions were optimized so each man's movement didn't interfere with the others. The loader stood on the left side of the breech, the assistant loader on the right. The breech operator, often the same person as the loader in well-trained crews, worked without complex coordination requirements. Everything about the weapon assumed that speed mattered more than theoretical perfection. Better to put 8 shells in a 100-meter circle quickly than to put 4 shells in a 50-meter circle slowly, because the 8 shells would suppress enemy movement and allow friendly forces to maneuver, while the 4 shells, no matter how precise, couldn't cover enough ground to prevent enemy response. The first M2A1 howitzers fell into German hands during the North African campaign, though initially in damaged or incomplete condition. Operation Torch, the Allied landings in Morocco and Algeria in November 1942, introduced American ground forces to combat against the Wehrmacht. American units were green, undertrained, and facing experienced Afrika Korps troops who'd been fighting in the desert for 2 years. The initial encounters went poorly for American forces in several engagements, but even in defeat, American units left behind equipment that German intelligence teams eagerly recovered. Most early captures were too damaged for detailed evaluation. A direct hit from an 88mm anti-tank gun or a fire that consumed the ammunition supply didn't leave much worth studying. But by February 1943, as American forces gained experience and began pushing through Tunisia, German units captured more intact equipment. The Battle of Kasserine Pass, in mid-February 1943, represented the Wehrmacht's last significant tactical victory in North Africa. Field Marshal Erwin Rommel's forces inflicted heavy casualties on inexperienced American troops and captured substantial amounts of equipment. Among the captured material were several M2A1 howitzers, some damaged but others relatively intact, complete with ammunition and in some cases the technical manuals stored in their ammunition chests. By May 1943, when Axis resistance in Tunisia collapsed and over 250,000 German and Italian troops surrendered, Allied supply dumps fell largely intact into the hands of Allied forces retaking the territory. But the brief period when German forces held these positions provided opportunities to thoroughly document and photograph American equipment before the final collapse. The Heereswaffenamt, the German Army Weapons Office, maintained a well-established system for evaluating captured weapons. Every major front sent technical intelligence teams, whose job was to recover enemy equipment that showed interesting features or represented significant capabilities. Anything deemed worthy of detailed study went back to Germany, usually to proving grounds at Hillersleben near Magdeburg or Kummersdorf south of Berlin. These facilities had been testing artillery since the Imperial German Army era. By 1943, they'd evaluated Soviet 76mm divisional guns, British 25-pounders, and various other Allied weapons. The process was systematic and thorough. Static inspection came first, measuring dimensions, weighing components, examining manufacturing techniques. Then came live fire testing with German crews trained to operate the captured weapon according to its original specifications. Finally, detailed engineering reports were written and distributed to ordnance bureaus, field commands, and industrial partners who might incorporate useful features into German designs. The M2A1 captured in Tunisia arrived at Hillersleben sometime in mid to late 1943. Initial reports focused on the obvious features: the split-trail carriage, the hydro-pneumatic recoil system, the semi-automatic breech. German engineers recognized immediately that this was a modern, well-designed weapon incorporating proven technologies. But the real revelation came during live-fire testing, when the rate of fire implications became undeniable. The Sicily invasion in July 1943 and the subsequent Italian campaign provided additional opportunities. The fighting at Salerno in September 1943 was particularly chaotic. German counterattacks nearly drove the United States Fifth Army back into the sea, and in the confusion of attack and counterattack, both sides lost and recaptured equipment multiple times. At least 3 M2A1 howitzers were abandoned during the initial beachhead crisis when American units fell back under heavy German pressure, then recovered days later as American forces pushed inland. These guns came with something even more valuable than the hardware itself. They came with American ammunition still stacked in ready racks, technical manuals still in their waterproof storage containers, and in one case, training materials that included crew drill diagrams and rate of fire standards. The manuals were in English, but the Wehrmacht had plenty of translators, including German Americans who'd returned to Germany before the war and now served in intelligence roles. More importantly, the manuals included detailed crew drill instructions, maintenance procedures, and the official United States Army rate of fire standards: 6 rounds per minute sustained fire, 8 rounds per minute for short-duration, high-intensity missions, 10 rounds per minute possible but not sustainable. German test crews initially assumed these numbers were propaganda, theoretical maximums published for morale purposes, but never actually achieved in combat conditions. Everyone who'd served in artillery knew that published rates of fire were aspirational. Real-world performance was always lower. Fatigue, ammunition handling difficulties, mechanical issues, all of these reduced theoretical rates to practical realities that were substantially slower. But when the Hillersleben test range assembled a crew of experienced artillerists and walked them through the American drill procedures step by step, the numbers held up. 6 rounds per minute wasn't theoretical. It was reliably achievable with a properly trained crew following the prescribed procedures. 8 rounds per minute required good coordination and rhythm, but it wasn't heroic effort. It was simply good crew drill properly executed. The test reports from late 1943 and early 1944 documented these findings with typical German thoroughness. Engineers measured breech operation timing from the moment of firing through ejection and readiness for the next round. They timed recoil cycle duration, tracking how long the barrel took to return to battery after firing. They documented crew loading sequences, identifying which steps took the most time and where the American design reduced crew workload compared to German equivalents. They compared the M2A1's performance against the leFH 18 firing under identical conditions with similarly experienced crews, same ammunition loads, same firing tables, same target scenarios. The conclusion was unavoidable and documented in formal reports that circulated through Wehrmacht command structures. The American weapon sustained nearly double the rate of fire of its German equivalent, and it achieved this performance not through superior crew training or extraordinary effort, but through design features that reduced crew workload and simplified the firing sequence. By mid-1944, additional M2A1 howitzers had been captured on the Eastern Front, where Lend-Lease deliveries meant Soviet forces were also using American artillery. The Germans recovered several guns during their fighting withdrawals through Ukraine and Belarus, as Red Army offensives pushed German forces steadily westward. Each captured weapon went through similar evaluation processes, and each one confirmed the earlier findings from North Africa and Italy. The German ordnance establishment now possessed a clear, documented picture of what they faced. American artillery doctrine wasn't just about fielding more guns, though numerical, superiority certainly mattered. It was about fielding guns specifically designed to exploit rate-of-fire advantages in modern mobile warfare. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The detailed test reports from Hillersleben paint a technical picture that extends beyond simple round counts. German engineers, trained to document everything with meticulous precision, measured the M2A1's performance across multiple variables that collectively explained its superior rate of fire. They timed the recoil cycle from the moment of firing until the barrel returned to battery position and was ready for the next round. 2.4 seconds on average. The leFH 18, by comparison, took 3.8 seconds for the same cycle. That extra 1.4 seconds might sound trivial in isolation, but multiply it across a 10-minute fire mission, and the difference becomes 40 rounds. Downrange versus 25. The semi-automatic breech operation saved another 1.2 to 1.5 seconds per shot compared to manual operation of the leFH 18's wedge block. The German breech operator had to physically turn a handle to unlock the wedge, pull it open, wait for the spent case to be removed, then close and lock it again before the gun could fire. The American breech opened automatically on firing, ejected the case, and required only closing and locking by the gun commander. Those saved seconds accumulated rapidly. The split-trail traverse advantage added another dimension. The M2A1 could shift 46 degrees left or right without moving the carriage, covering a wide engagement area. The leFH 18 needed full repositioning for anything beyond 11 degrees of traverse. In tactical situations where multiple targets appeared across a broad front, this difference meant American batteries could engage successive targets while German batteries were still unhitching, moving, and relaying their guns. The sustained fire tests proved particularly revealing about combat capability. German doctrine distinguished carefully between short bursts of rapid fire and sustained fire rates, because barrel heat, breech wear, and crew fatigue all degraded performance over extended periods. The test protocols at Hillersleben reflected combat reality. Fire as fast as possible for 5 minutes to simulate responding to an urgent infantry support request. Then maintain steady fire for 20 minutes. to simulate a deliberate suppression mission. Then, measure how long the crew and weapon needed to return to full readiness for another mission. The M2A1 crews consistently hit 6 rounds per minute during sustained phases, occasionally spiking to 7 or 8 rounds during the initial burst when the crew was fresh and ammunition was readily at hand. More significantly, the weapon itself showed no mechanical stress indicators. The hydro-pneumatic recoil system maintained consistent performance across all test firings. The breech mechanism didn't require additional cleaning or cooling after rapid-fire sequences. The barrel temperature remained within acceptable limits. The gun could theoretically maintain this pace as long as ammunition supplies lasted and the crew remained physically capable. The leFH 18 crews firing the same test profile peaked at 5 rounds per minute during initial bursts under optimal conditions, but dropped to 4 rounds per minute during sustained fire and eventually fell to 3 rounds per minute as fatigue set in. This wasn't because the crews were inferior. These were veteran gunners selected specifically because of their experience and skill. The performance limitation was the weapon itself. The leFH 18 demanded more physical effort and more time for each operation, and those demands multiplied across crew fatigue and stress. German engineers also evaluated ergonomic aspects, though they didn't use that specific terminology in their reports. They noted that the M2A1's crew positions minimized movement conflicts and interference. The loader and assistant loader worked on opposite sides of the breech, never getting in each other's way. The powder handler, responsible for cartridge cases, stood clear of the loading sequence at a dedicated position. The breech operator could perform his duties without requiring complex coordination with other crew members. Each man had a defined space and sequence that didn't overlap with others. The leFH 18, by contrast, required more choreographed teamwork. The breech operator had to manually close and lock the wedge block, then physically step clear of the recoil path before the gun commander could call fire. The loader and assistant loader had to work in careful sequence rather than parallel, because the box trail design created a more confined working space around the breech. Every second of coordination, every moment spent ensuring crew members weren't in each other's way, multiplied across crew fatigue and combat stress conditions. The ammunition handling tests revealed additional advantages built into American design philosophy. The M2A1's semi-fixed ammunition used brass cartridge cases that were relatively lightweight and easy to maneuver, compared to heavier separate loading systems. The cartridge case contained the propellant charge, and the projectile seated into the case mouth. This configuration allowed rapid loading while maintaining some flexibility for different charge configurations. German separate loading ammunition for the leFH 18 worked on similar principles in theory, but the practical execution differed significantly. German cartridge cases were heavier, the loading sequence required more steps, and the quality control variations across different manufacturers meant that crews sometimes encountered fitment issues that slowed the process. The test reports noted that after 100 rounds, the M2A1's breech required only basic cleaning to maintain reliable operation. The leFH 18 needed more intensive maintenance to clear propellant residue and ensure the wedge block seated properly. In combat conditions, that difference translated directly to sustained fire capability. American guns could keep shooting through extended fire missions without maintenance pauses. German guns needed more frequent cleaning breaks, interrupting the rhythm of fire support exactly when infantry needed it most. The tactical implications of this rate of fire gap became most apparent when examining how each side actually employed artillery in combat operations. American doctrine by 1943 revolved around the concept of time-on-target missions, usually abbreviated as TOT. The fundamental idea was elegant but devastatingly effective in execution. Coordinate multiple batteries, sometimes entire battalions or even multiple battalions, to fire at precisely calculated times so that all shells arrived on the target simultaneously regardless of how far each battery was from the objective. A properly executed TOT mission could drop 200 shells on a single objective in 30 seconds, The shock effect was overwhelming and psychologically devastating. German infantry, who survived TOT strikes consistently, reported that the experience felt like the ground itself was exploding. There was no warning crescendo, no gradual increase in fire that allowed soldiers to take cover or prepare psychologically. One moment you occupied a defensive position, the next moment everything within 100 meters radius erupted simultaneously. The psychological impact matched the physical destruction. Men who weren't hit by fragments were often rendered combat ineffective by concussion and shock. But TOT missions only worked if your guns could fire rapidly enough to deliver the required volume before the tactical opportunity window closed. If friendly infantry was attacking and needed enemy positions, suppressed during their final assault, you had perhaps 60 to 90 seconds to deliver enough fire to keep enemy heads down. Slow-firing guns couldn't generate the shell density that American TOT doctrine required. German artillery doctrine still operated largely on World War I principles, adapted through interwar study and early World War II experience. The emphasis remained on methodical barrage fire and carefully controlled fire missions. A typical German fire mission started with ranging shots. Forward observers identified a target, calculated coordinates through map study and estimation, and called for registration rounds. These were deliberate single shots, adjusted sequentially until they bracketed the target from multiple directions. Only after successful registration did the fire for effect phase begin, and even then, German batteries fired in careful, deliberate patterns designed to walk shells across the target area systematically. This approach maximized accuracy and ammunition efficiency. It minimized wasted shells. It demonstrated professional fire discipline that German artillery officers took pride in maintaining. It also gave enemy troops time to recognize they were being targeted and seek cover. By the time German shells were falling in effective concentration, experienced Allied infantry had already dispersed or gone to ground in whatever cover was available. The methodical approach that seemed professional and scientific in the 1930s had become predictable and slow by 1943 and 44. Counter-battery fire illustrated the rate of fire gap most dramatically, in tactical terms that directly affected battlefield outcomes. When Allied forward observers spotted German gun positions, which became increasingly common as Allied air superiority provided constant aerial observation, they called for immediate suppression. American batteries could shift fire, calculate firing data through efficient fire direction, procedures, and start putting rounds downrange in under 3 minutes from initial target identification. The first salvo might not be perfectly accurate, initial ranging was still necessary, but it didn't need to be precise. Volume compensated for precision in the suppression role. By the time German crews realized they were under counter-battery fire, shells were already impacting around their position. The rapid fire rate meant suppression was continuous and overwhelming. German crews faced two stark choices: stay in position and accept casualties, or displace immediately and cease supporting their own infantry. Either way, the German guns went silent exactly when their supported units needed fire support most desperately. When the situation reversed and German observers spotted Allied battery positions, the response sequence followed similar initial steps. Calculate firing data, shift guns if needed to bring the target within range, begin registration if the target was previously unengaged. But by the time German ranging shots started landing, American batteries had often already displaced using shoot and scoot tactics enabled by their truck mobility and rapid fire capability. The faster-firing guns could deliver their fire mission and reposition before German counter-battery fire became effective. The Normandy campaign in June and July 1944 demonstrated this dynamic at operational scale across continuous frontline combat. American artillery battalions firing in support of the breakout operations from the beachhead regularly executed mass fire missions, with 12 or more batteries participating simultaneously. German defenders consistently reported the effect as continuous thunder, a rolling barrage that never seemed to pause or slacken. Every attempt to move reserves forward, every effort to organize counterattacks, met with immediate and overwhelming artillery response. Wehrmacht artillery tried desperately to respond, but they were fighting both rate of fire disadvantages and severe ammunition shortages that had developed as Allied air superiority interdicted supply lines. Even when German crews had shells available, they couldn't match the volume American guns were producing. After-action reports from German commanders repeatedly mentioned being outgunned by Allied artillery. Not outranged, the leFH 18 could reach most tactically significant targets, but simply buried under more shells than they could possibly answer. One German division commander in Normandy estimated his artillery was being outfired 5-1, and he noted that this estimate was probably generous. Some American fire missions delivered 10 times more shells in the same time period against German positions. The Eastern Front showed similar patterns once Soviet artillery began incorporating American equipment and adopting similar mass-fire techniques. The Red Army received hundreds of M2A1 howitzers through Lend-Lease deliveries, and Soviet artillery doctrine evolved rapidly to emphasize overwhelming firepower delivered as rapidly as possible. German artillery on the Eastern Front, already struggling with ammunition shortages and crew casualties that mounted steadily through 1943 and 44, found themselves facing the same overwhelming volume they experienced in the West. By late 1944, Wehrmacht artillery effectiveness had degraded substantially, not because German gunners lacked skill or courage, but because their weapons and doctrine couldn't compete with enemies who'd optimized for speed and volume of fire. The German response to this documented inferiority followed predictable institutional patterns: engineering studies, modification proposals, attempts to retrain existing crews on improved techniques, and urgent requests for new weapon development. The Heereswaffenamt commissioned several projects in late 1943 and early 1944, aimed at improving leFH 18's rate of fire to close the gap with Allied weapons. One proposal involved retrofitting semi-automatic breech mechanisms to existing guns in field service. Engineers at Rheinmetall developed a prototype modification that replaced the manual wedge block with an interrupted screw design similar in principle to the M2A1 system. The prototype worked adequately in testing conditions. Rate of fire increased to approximately 5 rounds per minute sustained, a meaningful improvement over the standard 4 rounds. But implementation faced insurmountable obstacles that had nothing to do with engineering feasibility. Retrofitting thousands of guns already deployed across multiple fronts required factory time, skilled labor, specialized tools, and raw materials that simply didn't exist in sufficient quantities. By 1944, Germany was struggling to produce enough basic ammunition and spare parts to keep existing weapons operational. Breech modifications for marginal, rate of fire improvements couldn't compete for scarce resources against more critical needs, like anti-tank gun production, aircraft manufacturing, and ammunition production. The modification program was quietly shelved after prototype testing. Another approach focused on crew training reforms, attempting to extract better performance from existing weapons through improved human factors. If German gunners couldn't get better weapons, perhaps they could learn to operate existing weapons faster through refined techniques and intensive drill. The artillery school at Jüterbog issued new training directives in early 1944, emphasizing speed drills and streamlined crew coordination. Instructors developed new crew drill sequences designed to eliminate unnecessary movements and reduce time between shots. Units in the field received these new training materials and were instructed to practice the improved techniques whenever tactical situations allowed training time. Some units reported modest improvements from the enhanced training. Veteran crews who'd been sustaining 2 to 3 rounds per minute managed to reach 4 rounds per minute under ideal conditions, nearly matching their weapon's theoretical maximum. But training couldn't overcome fundamental mechanical limitations built into the weapon's design. The leFH 18's recoil system still required 3.8 seconds to return to battery. The manual breech still required physical operation by a crew member. The box trail design still limited traverse to 11 degrees. You cannot train your way past physics and mechanical engineering constraints. The training reforms also arrived far too late to matter strategically. By mid-1944, German artillery units were being filled with hastily trained replacements, many of them former Luftwaffe ground crew, whose air defense positions had been overrun, or overage reservists who'd never served in artillery roles during their original military service decades earlier. Teaching these men basic gunnery procedures and safety protocols took precedence over advanced speed drills. Simply getting replacement crews to operate the weapons safely and effectively was challenge enough without attempting to optimize their performance to theoretical maximums. Some German commanders attempted tactical adaptations to compensate for rate-of-fire disadvantages when they couldn't obtain better weapons or better trained crews. They experimented with concentrated battery deployments, putting more guns in smaller geographic areas to achieve higher local shell density, even with slower individual gun rates. If each gun fired half as fast as American equivalents, deploy twice as many guns in the same fire support area. This approach occasionally worked in defensive situations where German artillery could pre-register target areas and fire from carefully prepared positions with ammunition pre-positioned and fire missions pre-planned. But concentration also made batteries far more vulnerable to Allied airstrikes and counter-battery fire. A single, well-placed Allied fire mission could knock out multiple German guns that were positioned too close together. Allied fighter bombers, which operated with near impunity over German positions by late 1944, found concentrated artillery positions to be lucrative targets. The tactical benefit of concentration was often negated by increased vulnerability. Other units tried rapid displacement tactics, attempting to apply shoot-and-scoot principles with slower-firing weapons. Fire a quick mission of 10 to 15 rounds, then displace immediately to an alternate position before counter-battery fire arrived. This worked better than static defense in some situations, but it still couldn't match the volume that American batteries delivered. A German battery firing 15 rounds, then displacing, couldn't suppress targets as effectively as an American battery firing 40 rounds from the same position in the same time period before displacing. The German armaments industry did manage to field one new weapon design that partially addressed the rate of fire problem through improved mechanical systems. The 10.5 cm leichter Howitzer 18/40, essentially an leFH 18 barrel mounted on a newer carriage with improved traverse mechanisms and a modified recoil system. Production began in late 1944 after extended development and testing, but only a few hundred were manufactured before the war ended in May 1945. Even this improved model couldn't match Allied rates of fire because it still used fundamentally similar breech systems and crew drill sequences. The new carriage helped somewhat with rapid target switching by increasing traverse, but it didn't solve the fundamental issue of breech operation speed. Germany simply didn't have the time or resources to design and field a completely new howitzer optimized from the ground up for rapid fire on the American model. The V-weapon programs, V-1 flying bombs and V-2 rockets, were absorbing enormous resources that might otherwise have gone to conventional artillery development. Hitler personally prioritized these vengeance weapons, believing they would break British morale and change the war's trajectory. Whether conventional artillery improvements would have made any strategic difference is debatable, but the resource allocation decisions meant that evolutionary improvements to existing weapons were the best German industry could manage. By the final months of the war, from January through May 1945, German artillery had effectively conceded the rate of fire battle by simple lack of capability to continue fighting it. Ammunition shortages had become so severe that rate of fire became irrelevant. Units were rationed to 10 or 20 rounds per gun per day, sometimes less. At that level of supply, whether your gun could theoretically fire 4 rounds per minute or 8 rounds per minute didn't matter, because you didn't have shells to sustain either rate for more than a few minutes. The carefully documented test reports from Hillersleben detailing the M2A1's superior performance and identifying the specific technical features that enabled it gathered dust in Herauswaffenamt files. They'd become academic exercises, documenting problems Germany lacked the industrial capacity, technical resources, and time to solve. The lessons from those captured M2A1 tests didn't vanish with Germany's surrender on May 8, 1945. The Allied artillery performance in World War II became the foundational case study for post-war artillery doctrine development worldwide. NATO standardization agreements in the 1950s explicitly adopted rapid sustained fire as a core requirement for all member nation artillery pieces. The benchmark rate for 105mm howitzers became 6 rounds per minute, sustained with burst capability of 8 to 10 rounds. This wasn't an arbitrary standard. It was the M2A1 performance validated by 4 years of combat across every theatre where American forces fought. Nations joining NATO had to meet this standard with their existing equipment or commit to replacing their artillery entirely with weapons that could. The message from NATO standardization committees was absolutely clear. Precision without speed was obsolete. Volume of fire had become the defining characteristic of effective field artillery in modern warfare. West Germany's rearmament presented a particularly interesting case study in institutional learning. When the Bundeswehr formed in 1955, a decade after Germany's defeat, it faced fundamental questions about what artillery doctrine to adopt for the new German military. Former Wehrmacht officers were involved in planning and force structure development, and they remembered the rate of fire gap vividly from their wartime experience. The Bundeswehr didn't resurrect the leFH 18 or attempt to rehabilitate German World War II artillery doctrine as a foundation. Instead, they adopted American weapons and American training methods almost wholesale. The initial Bundeswehr artillery battalions equipped with, ironically, the M2A1 howitzer, the very weapon that had humiliated Wehrmacht artillery officers in 1943, purchased directly from American surplus stocks. German crews trained at American artillery schools, learned American fire direction procedures, and practiced American mass fire techniques. The weapon that had represented American superiority and German inadequacy became the foundation of Cold War German artillery. By the 1960s, when West Germany began developing indigenous weapons like the FH-70 howitzer in cooperation with Britain and Italy, the design requirements explicitly included sustained fire rates, matching or exceeding NATO standards. The FH-70 achieved 6 to 8 rounds per minute sustained, proving that German engineering could absolutely meet the rapid-fire challenge when it wasn't constrained by outdated doctrine and wartime resource shortages. The Soviet Union drew similar conclusions from studying captured German intelligence reports and their own extensive experience with Lend-Lease artillery. Post-war Soviet howitzer development prioritized rate of fire alongside range and shell weight as co-equal requirements. The D-20 152mm gun howitzer entering service in 1955 could sustain 5 to 6 rounds per minute, comparable to Western guns and far exceeding anything Germany fielded in World War II. Soviet artillery doctrine evolved to emphasize overwhelming firepower delivered rapidly, the same fundamental principle American gunners had demonstrated from 1943 through 1945. The Red Army's experience receiving and using thousands of American artillery pieces through Lend-Lease had convinced Soviet planners that rate of fire was a strategic capability, not merely a technical specification on equipment charts. The M2A1 itself served far longer than anyone in 1941 expected when it entered production. United States Army artillery battalions used it as their primary light howitzer through the Korean War from 1950 to 53, where its rapid-fire capability proved decisive in defensive battles. At Chipyong-ni in February 1951, surrounded American and French forces held off overwhelming Chinese attacks largely through artillery fire that never slackened. The M2A1 batteries fired continuously through the night, sustaining rates that kept Chinese assault waves from overrunning defensive positions. The gun saw extensive service in Vietnam, where its ability to deliver sustained fire support kept isolated firebase perimeters from being overrun during night attacks. Firebase commanders knew that as long as their 105mm howitzers had ammunition, they could generate enough defensive fire to break up massed attacks. The M2A1 remained in United States Army service until the early 1990s, when it was finally replaced by the M119, it itself, based on a British design but meeting the same rate of fire standards the M2A1 had established 50 years earlier. Many nations still use the M2A1 or licensed variants today in 2025. Total production exceeded over 10,000 weapons. For a design that began as a relatively straightforward modernization in 1941, that represents a remarkable service record spanning more than 8 decades. But the M2A1's real legacy isn't the longevity of the specific weapon system. It's the doctrine the weapon enabled and the performance standard it established that has shaped artillery development for 3 generations. Modern artillery has moved far beyond towed howitzers to self-propelled systems with automated bokers, loading, digital fire control, GPS-guided projectiles, and even more impressive rates of fire than anyone in 1943 imagined possible. The American M109 Paladin self-propelled howitzer can fire 4 rounds in under a minute, then displace before counter-battery fire arrives, using shoot and scoot tactics that the M2A1 enabled in primitive form. The German PZH 2000 self-propelled howitzer can fire 10 rounds in less than 60 seconds, using multiple round simultaneous impact modes, where the fire control computer calculates different charge and elevation combinations, so all shells arrive on target simultaneously despite being fired seconds apart. These extraordinary capabilities trace their conceptual lineage directly back to the World War II revelation that rate of fire often matters more than incremental improvements in accuracy or range. That German test officer standing at Hillersleben in 1943, watching a captured American howitzer outpace everything German artillery could field, he was witnessing the future of artillery warfare. He just happened to be on the wrong side of that future. The practical implications extended beyond abstract doctrine into the lived experience of soldiers on both sides. German infantry, by late 1944, had learned to dread American artillery above almost any other threat. They'd faced Soviet artillery on the Eastern Front, which was numerous and often effectively employed, but American artillery felt different to those who experienced both. The volume was relentless, the response time was immediate, and the accuracy improved constantly as American forward observers and fire direction centers refined their techniques. A German infantry company commander requesting fire support from his own artillery in late 1944 might wait 10 or 15 minutes for ranging shots to begin landing, then another 5 to 10 minutes for fire for effect to commence, assuming his artillery had ammunition available and wasn't already engaged with other missions. An American infantry company commander in the same situation expected and usually received effective fire support within 3 to 5 minutes of his initial request, with continuous fire available as long as the tactical situation required it and ammunition stocks held out. This difference in responsive fire support affected tactical decision-making at every level. German commanders knew that once they committed to an attack or a defensive position, they couldn't count on responsive artillery support. American commanders planned operations, assuming artillery would be available when needed, and they were usually correct in that assumption. The psychological impact on German soldiers was measurable in ways that went beyond casualty statistics. Interrogation reports from German prisoners of war consistently mentioned Allied artillery as the most feared weapon they faced. Not tanks, not aircraft, not even the feared American automatic weapons, but artillery. The reason they gave was the volume and the unpredictability. You couldn't hide from it. You couldn't fight back against it effectively, and it could arrive anywhere, any time, in overwhelming amounts. One captured German officer, a veteran of both the Eastern and Western fronts, stated in his interrogation that Russian artillery was heavy but predictable. You learned the patterns. You understood when it was coming and when it would stop. American artillery was different. It responded instantly to any movement, any concentration of troops, any defensive position that revealed itself, and it never seemed to run out of shells. The rate of fire advantage that German test officers discovered in 1943 became a tactical reality that German soldiers experienced daily by 1944 and 45. The technical superiority documented in proving ground reports translated directly into battlefield superiority that ground down German combat effectiveness as surely as any other factor. The story of the M2A1 howitzer and German recognition of its superior rate of fire represents more than a narrow technical comparison between two weapons. It illustrates how doctrine, design philosophy, and tactical requirements interact to create capabilities that determine battlefield outcomes. Germany entered World War II with excellent artillery by 1939 standards, weapons that had proven effective in earlier campaigns. But they failed to adapt their doctrine and weapon designs as the nature of warfare evolved. The methodical, precision-focused approach that worked in 1939 and 40 became increasingly obsolete as the war shifted to attritional conflicts where volume of fire mattered more than perfection of individual shots. America entered World War II with virtually no standing army and artillery that was obsolescent by European standards. But American designers weren't constrained by existing doctrine or institutional traditions. They could look at the problem fresh and ask what capabilities modern warfare actually required. The answer they arrived at emphasized speed, volume, and responsiveness over theoretical perfection, proved correct for the type of war that actually developed. The 8 rounds per minute that shocked German test officers in 1943 wasn't just a number on a specification sheet. It was a capability that enabled an entirely different approach to employing artillery in combat. It allowed time on target missions that could paralyze enemy formations. It enabled responsive fire support that gave infantry and armor the confidence to maneuver aggressively. It made counter-battery fire effective enough to silence enemy guns before they could respond. It created a tactical advantage that compounded across thousands of fire missions into operational and strategic superiority. The German officers who stood at proving grounds watching the captured Howitzer fire understood immediately what they were seeing. This wasn't just a faster gun. It was evidence that their entire artillery system, doctrine, weapons, and training had been surpassed by an enemy they'd underestimated. The American military had identified the right requirements, designed weapons to meet those requirements, and trained crews to exploit the capabilities those weapons provided. By the time German artillery officers recognized what they faced, it was far too late to respond effectively. The industrial capacity, technical expertise, and time required to close the gap simply didn't exist. Germany would fight the rest of the war, knowing that in artillery, as in so many other areas, they were outmatched by enemies who'd learned faster and adapted better to modern warfare's realities. The testing officer, checking his stopwatch in disbelief, was witnessing more than superior American engineering. He was watching the physical manifestation of a different way of thinking about warfare, one that would define artillery employment for the next 80 years and counting. 8 rounds per minute wasn't just impressive in 1943, it was revolutionary, and revolutions, once started, don't go backward. The rate of fire standard established by that olive drab howitzer with the white star became the baseline for everything that followed. A metal and hydraulic demonstration that in modern warfare, the side that shoots faster often wins, regardless of whose theoretical precision is greater or whose engineering traditions run deeper. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.